We have already seen that a hash function is only then a tool useful for integrity-related cryptographic purposes if the hash function is a one-way and collision-resistant function. If a hash function has these two properties, we call the hash function a cryptographic hash function. In that sense, it's clear that a hash function is not a cryptographic hash function and not useful for cryptographic integrity-related purposes if the hash function is either not one-way or not collision-resistant. Alternatively, and due to the relationship between collision resistance and second pre-image resistance, we also know that a hash function is not a cryptographic hash function if the hash function is not one-way or not second pre-image resistant. Let us look a bit more closely at the security property of one-wayness. One-wayness of hash functions, as a reminder, is the property we got to know as that it should be very easy to calculate the hash value of a certain input, but it should only be very difficult to calculate, given a hash value, an input that would map to this given hash value. This property of one-wayness is now an extremely fascinating property. Up until today, it remains one of the biggest unresolved questions in mathematics, logic, and even philosophy, whether one-way functions really exist, or in short, not a single function has so far been mathematically proven to be one-way. Given this, no direct attempts to prove the one-wayness of hash functions are usually conducted, but instead, hash functions like message digest 5, SHA-1, SHA-2, or SHA-3 that are developed by experts or have been developed through global competitions are often assumed to be one-way until proven otherwise. As a reminder, collision resistance, the second key property of cryptographic hash functions, is the property that it should be very difficult to find two different inputs of a hash function that would map to the same hash value. In order to understand how difficult it is to find two different inputs that map to the same hash value, let me very briefly tell you a story back from my time in high school. Back in high school, we were a high school class of 23 students. And one day, our mathematics teacher asked us to guess what the probability is that two of our class are born on the same day of the year. It turned out that for our class of 23 students, the probability that two of us are born on the same day of the year was just a bit more than 50%, which is a surprising result of probability theory now known as the birthday paradox. Asking the question about which day of the year a person is born is essentially just a mapping of people from the unbounded set of all people to the limited sized set of 365 days of the year. Once we understand this, it's quite clear that the very same mathematical thoughts underlying the birthday paradox can be applied to the world of hash functions and the collision resistance property. If we do this, we will find that if the size of the set of inputs is roughly the square root of the size of the hash values, then the probability is 50% that two of the inputs map to the same hash value. If our hash values are of length n bits, which really just means that we have a set of hash values of size 2 to the power of n, we then know that with a probability of just around 50%, we have a colliding pair of inputs if our input set is of size roughly 2 to the power of n over 2. Due to the core structure of hash functions, this is a result that applies to all hash functions and as such constitutes the baseline requirement that a hash function is only considered to be a collision-resistant hash function if a colliding pair of inputs can only be found if at least 2 to the power of n over 2 evaluations of the hash functions had to take place. If a colliding pair of inputs can be found with significantly less than 2 to the power of n over 2 evaluations of the hash functions, then the hash function is not considered to be a collision-resistant hash function. We have also seen that a hash function is not a secure cryptographic hash function if the hash function is not second pre-image resistant. As a brief recap, the second pre-image resistance property demands that given, for example, the x4, it must be difficult to find x1, which maps to the same hash value as x4. For this property of second pre-image resistance, no generic attack, like in the case of collision resistance, is known. And a hash function is second pre-image resistant if, for an attack trying to find this second pre-image x1, essentially no alternative exists than having to try 2 to the power of n different inputs if n bits is the length of the hash value that the hash function produces. After trying 2 to the power of n different inputs, the attacker is bound to have found the second pre-image x1, as after trying 2 to the power of n different inputs, essentially all available hash values have been exhausted. From this reasoning, we see that the hash function is not second pre-image resistant if an attacker can find the second pre-image x1 in significantly less than 2 to the power of n steps. With this solid understanding of security properties of cryptographic hash functions, let us now go back to the 4 most prominent real-world examples of hash functions, SHA-5, SHA-1, SHA-2, and SHA-3, and evaluate which of these 4 hash functions are still considered to be secure hash functions that can be used for cryptographic purposes. The property of being one-way, we now know, hasn't yet been mathematically proven for a single function, and hash functions developed by experts are assumed to be one-way until proven otherwise. Up until today, all of the 4 hash functions, SHA-5, SHA-1, SHA-2, and SHA-3, are still assumed to be one-way, and no generic methods exist to calculate, for a given hash value, inputs to the hash functions mapping to the given hash value. Similarly, for the property of second pre-image resistance, no generic attacks with significantly less than 2 to the power of n evaluations of the hash functions exist, indicating that all of the 4 hash functions are still assumed to be second pre-image resistant. The story is now very different for the property of collision resistance. For SHA-5, it has been expected within a few years of its release in 1992 that collisions will be found for SHA-5. The first real collisions were then found in 2004, and nowadays collisions for SHA-5 can be found within fractions of seconds on normal desktop computers, and even more, collisions can be deliberately crafted to look like authentic images, PDF, software, or even also X509 certificates. For SHA-5, collisions can now be found after roughly 2 to the power of 18 evaluations of the hash functions, where we know that due to the generic birthday attack, the baseline for collision resistance would be 2 to the power of n over 2, which in the case of SHA-5 would be 2 to the power of 128 over 2, or 2 to the power of 64. 2 to the power of 18 is significantly less than that, indicating that SHA-5 is not collision resistant anymore, and as such is not a secure hash function that can be used for cryptographic purposes. For SHA-1, let us briefly remind that SHA-1 produces hash values of length 160-bit. With the generic birthday attack, this creates a baseline of 2 to the power of 80 evaluations, after which colliding inputs for SHA-1 could be found. For SHA-1, it was assumed as of the mid-2000s that colliding inputs can be found with significantly less than 2 to the power of 80 evaluations. It then took up until the year 2017, when researchers at Google announced the first publicly known collision of SHA-1, with Google essentially presenting 2 PDFs that are very clearly very different optically, with one being a nice blue looking PDF, the other one being a nice red looking PDF, and both PDFs having the same SHA-1 hash value. From the research behind Google's attack on SHA-1, it can be seen that SHA-1 collisions nowadays can be found with roughly 2 to the power of 60 steps, which is significantly less than the baseline requirement of 2 to the power of 80 steps. From this, it's clear that also SHA-1 is not collision resistant anymore, and that also SHA-1 is not a secure hash function to be further used for integrity-related purposes. SHA-2 and SHA-3, on the other hand, are still assumed to be collision-resistant hash functions, which lead us to the conclusion that if you are constructing new systems and have to choose a hash function for integrity-related purposes, then message digest 5 and SHA-1 should not be used anymore, and that you should opt for either SHA-2 or SHA-3.